projects. In this video, we are going to explain the project Arrhythmia disease diagnosis based on ECG time frequency domain fusion and convolutional neural network. Introduction. Arrhythmia, a leading cause of global mortality and disability, underscores the critical need for early detection and treatment. This project focuses on improving cardiovascular disease diagnosis, emphasizing the importance of timely identification of arrhythmia symptoms. Electrocardiogram, that is ECG signals representing heart electrical activity, contain vital health information. Traditional diagnostic methods relying on human expertise face challenges in efficiency. This project explores the potential of convolutional neural networks (CNNs) to enhance arrhythmia detection by leveraging ECG signals. And existing ECG diagnostic methods are time-consuming and may underutilize information in both time and frequency domains. This project proposes a novel approach integrating time-frequency domain information using CNNs for more efficient and accurate arrhythmia diagnosis. And the project aims to develop a robust system for arrhythmia diagnosis through ECG time-frequency domain fusion and CNNs, benefiting healthcare professionals with improved accuracy and speed. The model's suitability for small devices also opens avenues for miniatured ECG signal-assisted diagnostic devices. Objective of the project. So, as I mentioned earlier, the project aims to develop an integrated diagnostic system for arrhythmia disease using a fusion of time and frequency domain information in ECG signals. The objective is to enhance the accuracy of arrhythmia diagnosis by leveraging both temporal and spectral features present in the ECG data. And the project seeks to compare the performance of convolutional neural network and long short-term memory models in diagnosing arrhythmia. And the project aims to utilize diverse datasets including MIT-BIH and PTD-BD for training and evaluating the proposed diagnostic system. The objective is to ensure the robustness and generalization of the model across different datasets, enhancing its applicability in real-world scenarios. And the primary goal of the project is to improve the recognition accuracy of ECG signals for arrhythmia diagnosis compared to existing methods. By incorporating both time and frequency domain information and employing deep learning techniques, the project aims to provide a more effective and accurate solution for identifying cardiac arrhythmias. Requirements needed to execute this project are software requirements. Software used is Anaconda, primary language used is Python, front-end framework used is Flask, back-end framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8GB and above, hard disk of 25GB and above. Now we'll discuss the working modules of flow of work. So the first step is importing required packages. In this step, we import libraries such as NumPy for numerical operations, Pandas for data manipulation, Matplotlib and Seaborn for data visualization, and TensorFlow Keras for deep learning. The second step is exploring the dataset. In this step, we import MIT-BIH and PTD-BD datasets and focus on understanding ECG images in NumPy format. We explore the structure of the data, inspecting the dimensions and characteristics of the ECG images. This step helps in gaining insights into the data before proceeding to further analysis. The next step is data processing. So in this step, we create Pandas data frames to organize and manipulate the data efficiently. We clean the dataset by handling missing values or outliers that could affect the model's performance. And we use Keras processing to prepare the ECG images for input into machine learning models, converting them into a format suitable for training. The next step is visualization using Seaborn and Matplotlib. So here, we employ Seaborn and Matplotlib to create visual representations of the dataset. We generate plots and charts to illustrate the distribution of classes, the characteristics of ECG images, or any other relevant patterns. Visualization aids in identifying trends and patterns that can influence model design and decision making. The next step is label encoding using label encoder. So in this step, we convert categorical labels into numerical format using label encoder. This step is crucial as machine learning models typically require numerical inputs. It ensures compatibility between the dataset and the algorithms. The next step is feature selection. Here we identify and select features that contribute significantly to the model's predictive performance. This involves analyzing the importance of different features in predicting the target variable, optimizing the dataset for model training. The next step is train and test split. Here we will split the dataset into training and testing subsets. The training subset is used to train the models while the testing set evaluates the model's performance on unseen data. The next step is training and building the model. In this step, we implement convolutional neural network and long short-term memory models for ECG image classification. Train these models on the training set, adjusting their parameters to learn relevant features and patterns associated with different cardiac conditions. And in the next step, that is extension phase, a hybrid model was created by combining predictions from multiple models for improved accuracy. So we will utilize the extracted and preprocessed data to train the mentioned deep learning models. These models will learn data patterns and relationships within the data. After the training phase, we will assess the performance on a separate test dataset using metrics like accuracy, precision, recall, and F-score to determine their suitability for real-world application. Additionally, a user-friendly Flask-based front-end with authentication was developed. And the next step is Flask framework with SQLite for sign-up and sign-in. So in this step, we integrate user registration and login functionalities into the Flask framework. Users can sign up by providing their information, and subsequently they can securely log in using their credentials. This enhances system security and allows for personalized user experiences. So after signing in, users provide input through the front-end interface. The input data is pre-processed to prepare it for prediction by the trained models. This pre-processing step ensures that user-provided data is in a suitable format for the model. And the pre-processed user input is fed into the trained models for prediction. The best performing model is selected to make predictions based on the input data. And the predicted outcome is displayed through the front-end interface, allowing the user to view the results of the model's predictions or analysis. Now we'll understand about the algorithms used. So the first algorithm built is convolutional neural network. So CNNs are designed for processing grid-like data like images by automatically learning hierarchical features through convolutional layers. These layers apply filters to detect local patterns, preserving spatial relationships within the ECG images. In ECG signal analysis, CNNs excel at extracting essential patterns from the spatial representation, making them robust for identifying complex arrhythmia-related features. The second algorithm built is long short-term memory, that is LSTM. So LSTMs, a type of recurrent neural network, are tailored to capture long-term dependencies in sequential data. They have memory cells and gates that retain information over extended sequences, making them ideal for time series data like ECG signals. In this project, LSTMs capture temporal dependencies within the ECG signal, allowing the model to understand the sequential nature of cardiac activity. LSTMs actively learn patterns in heartbeats over time, making them adept at identifying abnormalities or arrhythmias that manifest in the temporal domain. Now we'll see the comparison graphs of the models trained on MIT BIH dataset. So this is the horizontal bar graph comparing accuracies of different algorithms. In this graph on x-axis I have accuracy scores and on y-axis I have algorithm names. So accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. And this is precision score comparison graph. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. So precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall score comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. So recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F-score comparison graph. In this graph on x-axis I have F-scores and on y-axis I have algorithm names. So F-score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for predictions. Now we'll see the comparison graphs of the models trained on PTB-DB dataset. So this is the accuracy comparison graph. This is precision score comparison graph. This is recall comparison graph, and this is F-score comparison graph. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is the archive folder in which I have required dataset on which we will train the deep learning models. This is sample folder in which I have NumPy files on which we will make the predictions. This is static folder which consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. And these are Jupyter source files. These are Jupyter notebook files which contain combination of code, graphs and outputs all in one place. So Jupyter notebook file allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. Use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. So after running the app.py file, the Flask framework will host the application locally at the default address, localhost and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if you are new users, we have to register first. Fill in all these details and click on register button to sign up. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password. And click on login button. So it has redirected us to the prediction page, and here we have to upload our ECG signals. Click on choose file button. So from sample folder, I'm selecting the first one and click on open. Now click on upload button. So here we can see the outcome. So the heartbeat is detected as fusion beat, which indicates that two FOCI of pacemaker cells firing simultaneously. Now click on home link. We'll try again. Click on choose file button. This time we'll give another NumPy file. I'm giving this one and click on open. So the file is loaded. Now click on upload button. So the heartbeat has been detected as normal beat, and we can see obtained from ECG heart monitor looks like a smooth curve. Click on home link. Click on choose file button. So this time I'm giving this one and click on open. Now click on upload button. So here we can see the outcome, that is supraventricular ectopic beats, which indicates sinus rhythm with occasional irregular beats originating from the top of the heart. Click on home link again. Click on choose file button. This time I'm selecting this one and click on open. Now click on upload button. So here we can see unknown beat. Now click on sign out link. So the conclusion here is The project successfully introduces a novel method for arrhythmia diagnosis by fusing time and frequency domain information from ECG signals. This innovative approach enhances the diagnostic accuracy by leveraging both temporal and spectral features, providing a more comprehensive analysis. The incorporation of convolutional neural network and long short-term memory models proves highly effective in capturing spatial and temporal patterns within ECG signals. This combination demonstrates superior accuracy, showcasing the potential of deep learning for advanced cardiac health analysis. The extension of the project includes the development of a hybrid model combining predictions from multiple individual models. This ensemble approach contributes to a more robust and accurate final prediction, addressing potential limitations of individual models and enhancing overall performance. And the integration of a Flask framework provides a user-friendly interface for seamless input processing and presentation of diagnostic outcomes. The inclusion of SQLite for sign-up and sign-in ensures secure user authentication, enhancing the reliability and accessibility of the developed system. And the research significantly advances the field of arrhythmia diagnosis by proposing a method that surpasses traditional approaches. The comprehensive analysis of ECG signals, coupled with the utilization of deep learning and ensemble techniques, contributes to improved efficiency in identifying cardiac abnormalities, thereby offering a valuable tool for healthcare professionals in their diagnostic efforts.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.